really quite neat.
Yeah.
I'm going to take a picture of it.
And I also have another one in the car that's, if I go into an office, it's like a little, it looks like an arrow, a quiver that you hold your arrows in.
Okay.
But inside I can pull out the 2 foot wide and 5 foot tall banner, and then there's a little wire thing that holds that up. So yeah, we come out with quite a few interesting ways to display the evidence, the information. So.
Oh, do you want me to sit?
Yeah, that'd be good.
Right here?
Yeah, because then you might get in the shot.
I might get in the shot.
Yeah, let me see if you get in it, if you're sitting there. Oh, that's perfect.
Like your sense of humor.
Yeah, that's perfect. Perfect. Okay.
It's gonna take the
a little bit of
music.
Oh well.
That's all right.
Yeah, you know, sometimes you get copyright strikes on YouTube because of the
Background music.
I know, and that's what happened when I was down at the mall, the Quaker Bridge Mall. They had all of the Christmas carols playing, and it just they would not allow me to upload it or convert it so I could upload it to my other channel. So I have it on the one channel, but I couldn't put it on the other one. So I kind of lost interest in doing the malls.
Right.
But now I noticed that it was only a Christmas thing, that you don't really have music playing in the malls all the time.
Right. Huh.
So, I don't know. It's kind of dead now, though, in the malls. There's hardly any business going on there.
Right, because Christmas season's over.
Yeah.
Yeah.
So I'm thinking, well, maybe February, but
People are now recovered from their credit card bills.
overpaying, overbuying.
Right, right. Yeah, my wife and I, we're trying to get back on our feet as far as debt. You know about Dave Ramsey?
Yeah,
the finance guy.
Our church, the church I was going to at the time, they showed a presentation by him. Do you want to get anything started?
No, thank you. I actually just had lunch, so
Okay.
Thank you, appreciate it. So, you know, his story is a very interesting one of riches to rags to riches. But the thing I really like about his program is it's step by step, where, you know, finances, there's so many different things you could be working on. Like, for example, I'm married, with kids, with a house, and debt. And so it's like, I want to save for retirement, I want to save for college education, I want to pay off my debts, I want to pay off my house, I want to get rich, I want to save for big expenses. You know, it's like, well, how do you do all 5 things? And Dave's philosophy, his plan is that you don't do all 5 things at once. You do them one at a time. And it makes like perfect sense.
Right.
So
yeah.
So I just literally got the book like a week ago, and
I think there's a video series on it.
Mm-hmm.
Yeah, he has a lot of them. So, your first name is?
Charles. Sorry.
Charles.
I got a piece of ice in my mouth.
No problem. I'm Marilyn, and we're here at the January 20th at the Proper Brewery, and this is our meetup, and most of the Flat Earthers couldn't come today, but Charles showed up. So this is interesting. He allows me to record it, and we'll see how our conversation goes. So you're a globe believer?
Yeah.
Okay.
I actually started in the Flat Earth debate before Mark Sargent did, believe it or not.
Oh, really?
Yeah, March of 2008 was when I started in the debate.
And what prompted you to?
It was a thing on the Huffington Post, I think. The Huffington Post said, like, oh, Flat Earthers are coming out with their map. And, like, you know, of course, I'd heard about Flat Earthers, you know, dismissed them. And it was basically, it was a nice graphical display of the AE map. But, like, I didn't know Flat Earthers were a thing in the year 2008. you know, so I saw this thing on
that was quite a while ago.
HuffPo, and it was, so basically it's the background graphic. So if you take that background and take away all the lines, that was the image.
So the top.
No, this one.
That one with the blue
graphic,
and
with that exact graphic.
Oh, okay.
Because it was like with proper shading of the landforms. Yeah, so that's the Gleason.
Yes, it is.
Which I actually owned a 2 foot by 3 foot.
Yeah, I have that too.
Poster at home. Yeah, so that was my start, and then I started debating folks online, and it was really interesting because back then nobody used the word shell. Like the word shell was never uttered, and it was just people who disagreed about the shape of the Earth, and so people, you know, they had their different views and their different evidence that they wanted to bring to the table, and it was, you know, it was very collegial debate. But there wasn't any of the nastiness that is appearing in certain circles. You know, like somebody's a glober and they're like, well, you're a glober because you're being paid, you know. So it's like, oh, you're showing, you know. So it was interesting, the language.
Is there any way to turn this speaker off?
Yeah, let me ask the bartender.
So, and also the language changed. They use the phrase bendy light a lot. They never used the word perspective, and so now perspective has replaced bendy light in the debate. So it's just interesting.
And how about bendy door?
I don't know that.
There's a guy, Anthony Subrats from
Antonio Subrats.
Antonio Subrats from
London. Yeah,
and
I've
he
spoken
made
to
up
him
that word, the bendy door, about the ISS supposedly.
Oh,
opening
okay.
the door, it's really flimsy.
Okay. Yeah, so that,
And it was
yeah,
like,
that's a thermal blanket essentially on the outside.
A thermal blanket.
Yeah. Because when
But
you're
you can look right in. It is the only door.
Oh, it's not a hatch. Absolutely not. I don't know if I've seen the footage that he's talking about, but I have seen ones where the astronauts are coming out of the airlock, and then there's this flappy thing. It looks like it's made of cardboard or something. It's both for thermal and also for micrometeorites, because it's helpful to have like a second layer, you know, to stop, you know, just tiny projectiles like dust-sized micrometeorites.
Wow.
So yeah.
So what is your interest?
That's not the actual hatch.
Have you always been interested in wrong way?
No, that's right. You should turn.
No, it's
Well, no, it's actually a lot. It's a lot lower than it was. It went up. It went
up, and now it's. Did it go down?
Yeah, it went up and then down. That's all right. It's fine.
Yeah, I believe she turned it down.
Okay.
It's just the same control for the dining room, so you can turn it all the way off.
Right. Fair enough. Thank you. So, well, like everybody, I was raised with the globe and, you know, elementary school. You know, we're all taught the same stuff. But it was very interesting to me, the concept of how do you determine the shape of the Earth without, say, consulting NASA.
Okay.
And it was a Mark Sargent quote that he said. He was talking to some scientist, and he asked the scientist, he's like, how would you be able to prove to me that the Earth is a globe? And the guy was like, the only way to do it is to send you up in a rocket. And then so that got the wheels turning in my mind about like, how could you do it without sending somebody up in a rocket? And then that's where my channel came from. Is that
And what's the name of your channel?
Flat Earth Math.
Flat Earth Math.
Flat Earth Math. And it's dedicated to the math and science of the flat Earth debate.
Okay. Would you like some of this?
No, thank you.
Okay.
So it was an interesting challenge. It's like, how could you take an average person with no, you know, not a huge budget, maybe not near a coastline, you know, like here we are in the middle of Pennsylvania, we're, you know, 100 miles from the coast. How do you take somebody and have them be able to figure out what's the shape of the Earth, you know, without consulting experts? You know?
Right. Because we all know how honest experts are.
Yeah, and then my dad had this great phrase. He said, for every expert, there's an equal and opposite expert.
Yeah.
Let's take up one. Newton's second law, I believe.
That's right.
So yeah, I mean, you could debate over and over again. Like, I could bring my experts to the table, you can bring your experts to the table, and then the experts are going to argue, and it's like, would anything get settled? And I would say no. I mean, like, they're going to have people who agree with your experts and people who agree with my experts, but at the end of the day, I don't think anybody would be convinced by opposing experts. And so that's the thing with NASA and with, like, the Earth is a globe because of the photos from the ISS. Well, it's like, what if you say those photos are fake? Well, then that can't really be used as evidence if the evidence is dismissed. And so the point of my channel is to get people to get outside and take very careful observations and then figure out for themselves the shape of the Earth.
Okay.
And that's what I've...
So how do you propose that someone does that?
So it's basically observing the Earth, the sun, moon, and stars. And a lot of people misunderstand because they say you can't tell the shape of the floor by looking at the ceiling. And it's like, so we're not talking about the shape of the floor because of the shape of the ceiling. Like, that's not, because the shape of the ceiling outdoors is a dome. You know, like, no matter where you are, you look up and it's a hemisphere.
Okay.
You know, it's like every person's viewpoint. If you're standing on Earth, like, you're not if you're in a skyscraper or in an airplane, but if you're standing on Earth, you know, you can see a horizon and 360 degrees around you, and you can see 180 degrees overhead, and that makes up a hemisphere. So it's essentially a virtual dome around every person, right? And so it's like, so you could argue that the Earth is flat with a dome over it by looking at the sky. The sky looks like a dome. You can also argue the Earth is a globe because you look up and what we can see as a hemisphere is half a sphere. So it's like you got the celestial sphere. So here's the Earth and this is the celestial sphere. So it's like looking at the shape of the sky still doesn't tell you the shape of the Earth.
Right.
So that's not where my channel goes, and that's where a lot of people are like, oh, you can't tell the shape of the floor by looking at the sky. It's like what they're thinking of is the shape of the floor by looking at the shape of the sky. And that's not the focus, because the sky is always a dome. The sky is a dome, end of story. So what I propose people do is make careful measurements. Like, my favorite is the stuff you can do on the equinox. Like, I guess my #1 favorite of observation is taking a toothpick or, you know, something stuck in a pizza box or whatever, and you put it on a flat surface, and then you have the sun casting shadows out. You should use like a really small one so that the shadows will stay on your surface. And then from sunrise to sunset, you mark the shadows. You mark the end of the shadow. And we've all seen the time-lapse images of, like, you know, you've got something casting a shadow and the shadow moves in an arc. You know, I mean, we've all seen that video. You know, like the shadows moving and it seems to be in a curved line. So what I did is I'm a math teacher, and so I did the math, and I was like, what would the shadows look like if the Earth were flat? And it's like, well, it would be in a curve, because the sun's going in a curve around the North Pole. So if the sun on the equinox is going in a 12-hour circuit, well, then it would be, you'd have a curved path. You know, the sun's going in the curve. But then what I figured out was that if you have a globe, that the shadows would be in a straight line, which made no sense. Like, and this is me trying to figure it out myself, and it's making no sense to me. That the shadows would predicted to be in a straight line on the equinox. It's like, well, we've all seen the videos of the shadows being curved, you know, it's like, but it'd be a straight line. So it's like, all right, well, let's test it. And so I went out on the equinox and I marked the shadows for 12 hours. Well, it wasn't 12 hours, it was from when the sun was behind the trees or whatever. So it was as much as I could. And it was ruler straight. It was like absolutely straight. So it's like, could have been curved, turned out it was straight, you know? So it's like, it's those types of observations where, you know, it's just a little piece of evidence. It's not a deal breaker. That one piece of evidence does not prove anything. But it's an interesting piece of data for the shape of the Earth.
So that's only on the equinox?
On the equinox, it'll be a straight line, and actually on the June solstice, it'll curve one way, and on the December solstice, it'll curve the other way. So it'll be a smiley face, and then 6 months later, it'll be a frowny face. And on the equinox, it'll be a straight line. There's a lot of stuff you can do with sundials. It's just really fascinating.
It's March and September.
March 20th, 22nd.
March and September are the
equinoxes, right.
June is the summer solstice, and December's winter solstice.
Right, right.
Yeah. Okay. Straight line. I just started, let me see.
You're gonna get us kicked out?
Just a little plug.
I didn't see
so
anything.
Anyway,
Hear anything.
so I just started taking measurements of the compass readings at sunrise, at daybreak, and sunset.
Using a compass.
Using a compass, and that on the equinox, it was a little surprising to me that it was due east.
Yeah, pretty close to due east. I mean, compasses are going to be a little bit off a magnetic compass.
Yeah.
But,
so then in December, I did it again, and it was more further south.
Right, south of due east.
I have also people in South Africa who also did a compass reading on the equinox, and hers was due east from South Africa.
Right.
So I thought, well, that is a little strange to me. I thought it would be a little further north.
Right. Especially since the equinox, you see 12 hours of sun. Like that's the key.
Her sunset, the evening before the sunset, was way south.
South of due west. And it rises south of due east.
So
yeah, that's a head scratcher.
I'm not sure. So I thought, okay, I'm not going to make any false judgments or rush to judgment. I'm going to get more data.
Mm-hmm.
And that's what I'm doing now. And I'm encouraging others in the Flat Earth community to get more data.
Bingo.
So then, I've also been in contact with a science group.
Mm-hmm.
Guys who are, and I think there's one girl science teacher. I don't know what school district, but she is a current science school teacher. And there's a bunch of guys who are in the science field, electronics and that sort of thing. So they all have this in common. And then they get online. They do a movie night where they're all drinking and, whooping it up.
Right.
So I'm not interested in that. But they have allowed me, the one guy came down to Ocean City Boardwalk while we were down there one time. And he approached me and had a cameraman and wanted to record what was going on.
Okay.
And so we kind of had a conversation and we struck up a little acquaintance, and so now there's a little hangout where I can go on and ask them questions. Mm-hmm. And so we have a little bit of a relationship there.
Yeah. That sounds very
I try to get along with people, and it's not antagonistic. They are not allowed to laugh at me or anything like that.
Right.
So that's one of the rules. So I am interested in gathering this data. I think there's some things that I'm not sure if we're going to be able to figure out. But I do know that water is always flat. So it's always flat on the surface.
What I would argue, water always appears level. So it's like there's a lot of truisms in the flat Earth debate that are based on things that are like mostly true. Like, for example, water is always level. I would say water is always locally level, and all water always appears flat. So I would agree with those two statements are perfectly true. Water is always locally level and water always appears flat. Bingo, that's the truth. But that doesn't translate into mathematically flat or infinitely level.
Okay,
you know?
Mathematically, now you're a math teacher. So what is the curvature formula for your globe?
Yeah, so you could approximate with 8 inches per mile squared is actually a very, very good approximation. And what people misunderstand with that calculation is that doesn't tell you how far you should see, because the 8 inches per mile squared, it's like, you take, just pretend it's just a sphere, and so you've got, it's a tangent, so it's like wherever your observer is, that 8 inches per mile squared, you have this line, and this line is literally shooting out into
straight
space.
Out, right?
It's going straight out into space, and then we're measuring from that line.
Right.
So it's like if you look at something far away, you can't see the line that's shooting out from beneath your feet. Like you can't, there's no dot on the horizon that says, this is a projection, and then we're going to measure down from there. It's just, all you see is horizon, sky, sea, whatever.
Correct.
And so what people do is they photograph something on the horizon, they photograph distant buildings, distant mountains, distant islands, and they're like, well, according to 8 inches per mile squared, but it's like 8 inches per mile squared is just mathematical curvature from this tangent. It doesn't tell you how far you should be able to see.
Correct.
Now you can figure out how far you should be able to see if you put your observer height in.
Doesn't that observer height and how
is key.
well are your eyes working?
Well,
you know, because
but then you substitute a camera, and it sees the same thing.
Okay.
So it's not dependent on human vision.
Okay.
Because you throw a camera in there, if the camera sees the exact same thing you do, only with greater clarity, then it's not a humans can only see so far, or our eyes work.
That's very correct. That's true.
So.
Okay, and that's what we're doing is experiments with the P900 and P1000.
P1000, sure, it's a great camera for long distance viewing.
Yeah. So so if we have, like, I always use the example when I'm teaching is when I go to Wildwood, I can see Atlantic City. Yeah,
and when you go to, what's that, Rehoboth Beach, you can see the lights that glow on the horizon of Wildwood. I don't know if you know that, but it's like 6 miles. I'm sorry, I'm interrupting your story.
That's all right. You're
but
allowed.
I just was at Rehoboth Beach this summer, and I looked it out on the map, and I'm like, oh my goodness, I didn't realize that Rehoboth Beach is in Delaware, and I did not know that Wildwood is like the southernmost tip of New Jersey, I think. I mean, it's the southernmost tip of a piece of New Jersey, not necessarily the whole state. So, and there's this wide inlet, and I think it's 6 miles from Rehoboth Beach to Wildwood. And also, my understanding is that Wildwood is it's like an amusement park practically. There's beaches, but there's roller coasters, there's lights, there's a boardwalk.
Right.
Well, you can't see a single light from Rehoboth.
All you can see is a glow.
Oh, you see is a glow on the horizon. You see the horizon, you see a glow that's,
Okay.
but it's 6 miles. So it's like, according to, and if I'm standing on the beach, so my observer height is not too high above the water,
Okay.
then I shouldn't be able to see it, and I don't see it, things like that.
Right.
But if I were to increase my elevation, Rehoboth Beach doesn't have any hotels or whatever, 20-story hotels. But if you get up high enough, you should be able to see the lights.
Right.
Theoretically.
And also, when you're in Wildwood, you can see Atlantic City.
Okay.
So that does have hotels.
Right.
And the problem in the summertime is that you have atmospheric conditions that might...
Right. They kind of mess things up.
Yeah, like a fog. And over that distance, you're going to have a lot of moisture in the air.
Mm-hmm.
And then there's also something I learned about, which was compression in the image compression.
Mm-hmm. Yeah, it's a mirage type of factor, but yeah.
Angular resolution. You cannot distinguish the items because the angle is too small.
Yeah, there's a couple problems with angular resolution. A lot of people don't realize the best example I can have is you take a newspaper or even a book, and you open a book to a 90-degree angle, and then I think it works better with a newspaper because the newspaper, the writing is written this way. So you open it up at a 90-degree angle and you place it at a table, maybe prop it up against the wall, and it's like, so I should be able to see the the part of the newspaper that's sort of facing me.
Right.
But the part of the newspaper that's lying flat on the table, it's like the text is all going to run together. Now, if I lower my vantage point, that text is going to completely just turn to gray.
That's correct.
But the text that is facing me on the wall, you should be able to see the bottom line of text.
Yeah.
So it doesn't matter how high or how low you go.
That's correct.
You should be able to see the newsprint that's facing you, whereas the newsprint that is on the table, you have to get a certain height, and then that's where your angular resolution comes in.
Right.
But a lot of people don't understand it. They're like,
I didn't know until I heard about it, and then I started to look into it.
Mm-hmm.
But it is part of perspective, and I had really put a lot of study into perspective, so that was easy for me to grasp what that was.
Now, when you say perspective, do you mean like vanishing point perspective, like Renaissance, where you're drawing something and all the lines go back to the vanishing point? Or are you talking about perspective in terms of like the flat earth debate perspective? Because the word perspective can mean many different things.
Yes, it can.
In the flat earth debate.
Isn't that interesting?
It's almost like a catch-all.
Yeah. So I'm talking about how your eyes see at a distance.
Okay.
And the vanishing point, but when you're talking about a horizon without anything obstructing, it's a vanishing line.
Yeah, well, the thing about the vanishing point is, the analogy is like a chessboard. Well, all the lines in the chessboard, they're all parallel to each other or they're perpendicular to each other. But there's nothing that says that you can't take another chessboard and put it next to the first one and just put it at an angle. In which case, if you take a photograph of that, there will be two vanishing points. The first chessboard will have its own vanishing point. The second chessboard will have its own vanishing point. And they both will be on the horizon, or near the horizon. But a lot of people don't. Like, there was this one drawing I found. I just looked up vanishing point or like perspective, and I found this drawing that was done in a computer, and there was like 12 different vanishing points in that drawing. And it was a drawing of a staircase. It was like an architectural drawing where it was in 3D rendering, but like the treads, they all went this way. But then we had the risers. Well, they all went this way, and then there was different pieces of it, and there was multiple points of multiple vanishing points. It was really quite a eye-opening image.
Right.
There isn't just one vanishing point. There's one vanishing point if you have a bunch of parallel lines. They will all go to the same vanishing point.
Or if you have a plane meeting another plane, then you have that one vanishing line because there are no four planes. When you have two planes, you get the line. When you have four, which is like railroad tracks, each of those tracks is a plane coming to a point. That's where you get a point, when you have four planes.
Yeah, well, no, where two planes will meet produces a line, which you just said. But the railroad tracks, they're not planes, they're lines. And they actually never meet. They appear to me.
Well, that's the whole thing with perspective,
go as many miles as you want. Those railroad tracks aren't just going to come together.
I know, that's what I teach.
So they're. So what do you?
So
when you
I'm a flat Earth geography teacher.
Oh, okay. Very interesting.
So when you have a plane here and a plane here, these never meet.
Okay. So they are.
They never meet.
They're okay.
But they appear to meet.
I get you.
The railroad tracks never meet, but they appear to meet.
Bingo. I got you.
Okay.
I got you. So that's where the horizon comes from.
That's exactly right.
The sky is a plane, and the land's a plane. Then
but they never meet.
There is a vanishing
line.
I get you. I never heard of that. That's really ingenious.
Yeah.
That's really cool.
So when I first started learning about flat Earth, that was one thing I put a lot of time into, was studying perspective, because it just didn't make sense what we were told, and I didn't know what I was looking at. So I had to put time into researching perspective, so I knew what I was seeing.
Right.
Because you don't know what you're looking at. You know things like, they appear to get smaller, but in your mind they don't. Those telephone poles, they don't get shorter, but what you're seeing is something very small down the end.
So along with the topic of what did you say, angular resolution, is the angular size. And that's really, that ties exactly into perspective. And do you know about the angular size formula? And there's calculators, and it's a simple math equation where it's like, if you've got something at a certain distance and you know its height, then it's going to make a certain angle, you know, like a camera angle, you know. You got a viewer, and then this thing, so like maybe that angle is like 5 degrees. Well, then you pull it further back. Well, that angle now is like 4 degrees. Pull it further back, and now it's 3 degrees. So at the angular size, so and you can take an image, and you can actually measure on that image the angular sizes of things. If you know, like if you've calibrated the camera, that's one of the things I try to have people do on my channel, is go to a football field and take a sheet of paper and then photograph it at 100 yards, like, and take the actual photo, the JPEG, and say how big is that sheet of paper at exactly 100 yards? How many pixels tall is it? How many pixels wide? And you can actually figure out what's the angular resolution of your camera, not the resolution, the angular size.
Yeah. And
you can actually do math with that. Then you take that same camera, same zoom, photograph the moon. You're like, well, the moon is like 470 pixels wide. Well, you can actually translate that into how many degrees that is. And so that's...
The problem with transferring that to the moon is you don't know the size of the moon and you don't know the distance of the moon.
Well, but what my point is, you're correct. What my point is you can actually tell the angular size of the moon, regardless of its distance or size. You're exactly correct. You can tell the angular size of the moon. And then you can do the same thing with constellations. What's the angular size of Orion? Like, how tall is Orion?
Have you seen, like, these so-called pictures from outer space where the Earth is this size and then the moon is in front of it this size? Right,
the one from the epic the Discover satellite. And it's approximately 1/4. It looks
so.
like the moon
does that
1/4.
compute with you when the guys were on the moon, in quotes here, and they took a picture of the Earth, which was this size?
Yeah. So you know that lenses come in a million different varieties.
Okay, so it's the camera?
But the thing is, if you're going to be comparing pictures, you have to ask questions about the lens. So for example, the lens that they use on the Discover, it's an extremely small telephoto, or it's extremely long telephoto. What am I trying to say? Extremely long focal length, which means that because the Earth is, I think, 1 million miles away, and so...
The Earth is what? From the moon?
No, from the EPIC satellite.
The satellite.
The EPIC satellite that you talked about, where the moon passed in front of the Earth.
Right.
So the question is, what was the lens that they used? Right. So whenever you talk about a photo and you want to say, well, look at the size of this thing in the photo, the number one question you should ask is, what was the lens that they used? Like, I mean, you're welcome to talk about what's the size, but if you don't know the focal length of the lens, you can't make an apples-to-apples comparison.
But if something is a proportional size to another object, shouldn't the proportions remain the same?
Absolutely. But if you move your vantage point, for example,
but the proportion won't change.
But if you move your vantage point, the angular size will change. So for example, and this is not going to be to scale, because the map is not big enough. Okay? So we have, and like I said, the moon is actually way out here. So this is not to scale. But so like, let's say here's the moon, here's the Earth. If I'm in orbit, and again, this is not to scale, the ISS is actually a lot closer. But if I have a camera on this satellite, how big is the Earth? Well, the Earth is going to be like a 90-degree angle, right? Well, now I put a camera over here on the moon, how big is the Earth? It's only going to be a few degrees. Okay? So nothing's changed. The sizes of anything has changed. The observer location has changed. And then you take the observer and you turn him around, face him towards the moon. And it's going to be another angle. Well, now you put him in orbit around the moon, and then the moon is now huge. You know? So the actual sizes of them are changed. So you're absolutely right with proportional sizes. Yes, the proportional size won't change, but the angular size, like how close you are to something,
yeah,
something is going to look bigger.
I agree about angular size, but that really has little to do with the proportion and of the two objects. That should be the same, and has not much to do with the flatness of the Earth.
Yeah.
So
You're right about it doesn't have to do with the flatness of the Earth. It does have to do with whether or not those images make sense or not. But I hope you get the point that if you move the camera around,
you're changing the angle.
You're going to change the angular size. Like if I had a camera,
I understand.
Where you're sitting, well, here the angular size of the moon, the angular size of the Earth is appearing from your vantage point. The Earth appears 4 times bigger than the moon. Well, now you zoom that camera in and put it right next to the Earth is going to look like it's going to fill the frame, whereas the moon is going to be now this dot.
Did you ever take a feature on the moon?
What do you mean? Like, the man in the moon, you see the light and dark areas.
So-called craters.
Yeah, I don't have good, my camera is several years old. Like, my camera's like 5 years old.
I think it's I can see the man
in the moon, but I can't see any, I think I could see some craters. It depends, it's not on a full moon. It has to be like a quarter moon or crescent moon. You can see some craters on the...
See, there's going to be a problem whenever you look outside of the surface of the Earth, is you really don't have an idea of the size of the objects in the heavens, nor the distance, even with the sun. When I teach, I say the sun is 9.3 miles away.
9.3 miles? Okay.
Yeah, and it sounds amazing or it sounds ridiculous, but I think we're gathering some information which is proving that to be more realistic.
So, and I'm just going to play devil's advocate.
That's fine.
So you've said you've talked to people in South Africa at their sunrise. Now, obviously, their sunrise it's not at the same time as ours, because South Africa is here and then we're over here. But what's due north of South Africa? Well, it's Europe. So is it possible that somebody in London, London isn't necessarily due north of South Africa, but so Europe is right here, and then South Africa.
Isn't that interesting though? I remember seeing maps when I was little that South America was directly underneath Central America. And yet now when you look at this, it's way off to the side.
Yeah, well, if you show a Mercator projection, did you say South America versus what, Central America or North America?
Yeah.
Because it kind of
it was like in a line,
around.
But now it seems like it's really shifted way far over, like on that.
Yeah, well, if we had a Mercator projection, I'd be able to make a better comparison. But the point I was trying to make is, let's say you have your observer in South Africa and you have an observer in someplace in Europe that's north of South Africa, and they both look and they both watch the sunrise, right? So I hope you would agree with me that South Africa is thousands and thousands of miles away from London. So if the sun were 9 miles away, how could two observers who were thousands of miles apart be looking in the same direction? Do you see what I'm saying?
Well, they could actually see the sun if it was very bright, and like it is, and if it were a flat surface.
So, but where would the sun be at that location?
Well, see, this is what I'm still trying to figure out with the compass readings, because if it's a circle, then how close does it have to be, and where will they start to see it, and that sort of thing. If it's coming around, I can see where if I'm here and it was coming around, then I might get it due east. It might not be.
Yeah, well, the thing about the circle, and this is the wonderful thing about the equinox, is that the sun is in the sky for 12 hours. Maybe give or take 15 minutes. I mean, the math is not 100% perfect, but the sun's not in the sky for 10 hours. It's not in the sky for 14 hours. It's in the sky for 12 hours on that day, give or take a few minutes. So that means if you have a circle representing the path of the sun, now in this image, that's the yellow circle. So the yellow circle is the equator. The white circle is the Tropic of Capricorn. The red circle is the Tropic of Cancer.
Do you know what the white part is around the outside?
Oh, well, that's the Antarctica / ice wall, But so if you just look at this yellow circle, that's the path of the sun on the date of the equinox, right? And if you see the sun for 12 hours, that means that if the sun, like let's say if you were down here in South Africa, the sun was going to appear to rise, it's going to be here, and then it's going to appear to set when the sun's over here. It has to be a 12 hour, it has to be exactly half of that path is where the sun is going to be.
Yeah.
So then you're going to have a really hard time getting a due east or a due west You know, but the question that I had for you is like the distance. If the sun is 9 miles away, like two observers who are 9 miles away, they should see the sun in a significantly different place in their sky. You know, like you could get 10 people, like, you know, somebody's 9 miles away, or like say round it up to 10 miles, somebody's 20 miles away, somebody's 30 miles away. Like, let's all look at the sun. Let's all take an exact compass reading and an angle of azimuth.
That's what I've been trying
you know?
to do, and I don't know that we're going to get that. Some people are not as interested to find out.
Right.
You know, they just want to get through the day, and I think that's by design. But okay, so when I get back to Wildwood and I look up at Atlantic City, and that's 32.6 miles away.
Okay.
So that should be hidden. Atlantic City should be 681 feet.
Well, that's only according to the 8 inches per mile squared.
Correct.
Which
now,
is not,
explain
which
to me
is not
why,
a measurement of how far you can see.
No, it's a measurement of how far is hidden.
And I'm sure you're familiar with the online calculators. There's the Earth Curve calculator.
That's correct.
There's one on GitHub. There's one on Metabunk. And I'm sure there's a couple other, and you can actually write your own.
So what do you think that 681 is then?
Well, so mathematically, you take this, you take a sphere, and you take a line. Like, let's say, you know, you're standing here you say you're in Wildwood, and then you place a line underneath your feet that is tangent to the globe, right? So that line, of course, this is not to scale, but that line is going to shoot out into space. That the Earth is going to curve away from it.
Correct.
But you're not going to see. I'm so sorry. Come on. You're not going to see. Like, if you look at the horizon, you're not going to see a projection of what's underneath your feet. This plane. It's a theoretical plane, right? It's tangent to the Earth. It's theoretical. That's the 8 inches per mile squared. How fast does the Earth curve away from this theoretical line? 8 inches per mile squared is a pretty good estimate. But you don't see this line because this line doesn't exist. This line is not a line of sight.
Okay.
It is a theoretical line.
So what does that
to the Earth.
681 feet represent?
The distance from that line, which is the theoretical line, doesn't exist. The distance from that line to the surface of the Earth. You know, so many miles away.
So I should not see a 67-story building then?
No, because that's not a line of sight. We're not measuring that 600 feet from a line of sight. We're measuring it from a theoretical line that doesn't actually exist in the real world. All right? So
if my face were down on the ground.
Oh, if you were at zero, if your eyeball was in scuba, they have this thing called halfies. Have you ever heard the term halfie? So if you have a camera, an underwater camera, and so you're taking pictures underwater, but like the housing is such that you can lift it up and you can take a picture above the water. Well, if you lower it so that the camera lens is in the water, you get a really neat picture. You can see sky and trees, whatever, and you can see fish. Okay. And it's called a halfie. So if your camera is in that position, where literally the water is crossing the center line of the lens, then 100% 8 inches per mile squared lines up with that sighting.
So when I'm taking a happy picture, I should not see
Atlantic City. That's correct.
Okay.
But nobody takes happy pictures.
And what difference does the height of my eyes make? If I am standing 5 or 6 foot above the surface of the happy water,
right?
Shouldn't I just add 6 feet onto the other side?
No. Not unless the horizon was exactly halfway between you. If the horizon was exactly halfway between you and your target, well then yeah, if you rise up 1 foot, then the line should, it's like a seesaw. If you rise up 1 foot, it should go down 1 foot. But we're talking about an observer that's very, very close to the horizon. Like the horizon's only about 3 miles away.
The curvature formula does not tell you where the horizon is.
The curvature formula is based on the geometry of the globe, and the geometry of the globe can tell you where it is. So you could work it out. You could backwards work it out.
The curvature formula tells you how much is going to be hidden.
No, it's not a visible hidden formula. It's just a pure mathematical curvature. So that's where you need to use either Metabunk, GitHub.
Well, The Earth curvature calculator gave me the 681. It's the same formula they use.
Well, no, that would be the drop. If like
okay, you want to call it drop? That's
right,
fine.
Right, which is not obstruction. So drop is not obstruction.
Okay, what is obstruction?
So obstruction is dependent on your observer height. So for example, just
let's get to what it is.
If you had like a hotel, like a 10-story hotel, and it's right on the beach, and let's say it's like really close to the beach, and if you were at the bottom floor of that hotel and you were saying, well, I want to look at Atlantic City, which is how many miles away?
32.6.
Okay, so it's 32.6. Well, what is Atlantic City from the top of the hotel? It's still 32.6 miles away. Like, you haven't changed anything. But I'm pretty sure that you can see Atlantic City from the top of the hotel. You can't see Atlantic City from the bottom. So in other words, the Earth curvature has not changed, but the obstruction has changed. Atlantic City would be completely obstructed down at the beach, and I'm just doing this off the top of my head.
That's fine.
But at 100 feet elevation, you know, your sight line, you know, you're increasing your sight line height, so your sight line, you should be able to see more and more and more of Atlantic City.
And I think you're seeing more and more and more of things at a distance because of the angular resolution and the less atmospheric interference.
Yeah.
Because I'm here to tell you as a witness that I can see Atlantic City from Wildwood.
From what elevation?
The boardwalk or
okay.
on the beach.
Yeah. I would just need to know. Well, the thing is, Atlantic City has skyscrapers, not skyscrapers, but I mean they've got 20, 30 story
to the shore.
So,
and this is the kind of footage we're getting.
Yeah.
We've got footage of great distances, and we're getting